Considering our interlinked tank system here again, and its standard form with a non-homogeneous part, how would we go about predicting what the concentrations A and B are going to do over time? Well, what we're going to need is the eigenvalues and eigenvectors of A to get the corresponding homogeneous solution. Let's call this our vector x and x here. To find xc, we find the eigenvalues and eigenvectors of A. And for that, it's not a complicated calculation with a 2x2 matrix, but we'll automate it here. We end up with two values, negative 0.06, and the other eigenvalue is negative 0.21. The corresponding eigenvectors are 2, 3, and the second eigenvector is 1, negative 6. So fairly nice values here. What do we do with that? Well, we can build our solution for the corresponding homogeneous part, everything up to, but not including the 2.1 here. We have two exponential decays with some scaling factors and some arbitrary constants out front. And that would be it. That would be our corresponding homogeneous solution. Next, we need the solution that's going to work with the non-homogeneous part. We'll do that on the next page. Considering the differential equation again, we look at this right-hand side, or this non-homogeneous part, and we look for its differential family, which is simply the constant family. All we have is constants here, so we're good to go. We assume that our non-homogeneous solution type is just 1, that constant solution, times some vector that we don't know u. And then we sub that into the differential equation. Well, the differential equation is listed out here. The first term is really easy. It's just the derivative of that constant vector, which is going to be 0. Then we have all our coefficients, and we work with those, times, let's call it u1 and u2 now. They will play a role in this side, plus 2.1 and 0. This left-hand side is just the 0 vector, and so we end up with a linear system of equations. Negative 0.09, 0.02, 0.18, negative 0.18 times u1 and u2, and we just bring this to the other side so it becomes negative 2.1 and 0. Now before we solve this, let's go back one page and look at this solution here. This solution has two elements that go to 0 as t gets larger and larger and larger. But what do we know about the system in reality? We know that water's coming in with a concentration of salt of 30 grams per liter. So in the long run, all the water, whatever it is, high, low concentration to start with, doesn't matter, it's going to be flushed out and we're going to be left with 30 grams per liter. So when we start solving this, we're going to find, pretty much guaranteed, that we're going to get 30 and 30 for u1 and u2. But let's verify that. If we take 2 times this equation here and add it to the second equation, these terms cancel, and we get 0.04 minus 0.18, which is minus 0.14 u2 is equal to 2 times this, which is minus 4.2. And that gives us, as predicted, 30. And again, the concentration, or the values we're talking about here, this is a solution, so it's a concentration in grams per liter. So we get 30 grams per liter. Likewise, with a bit of work, we can solve for u1, which is also going to be 30 grams per liter, just by back-subbing in. And so that gives us our x non-homogeneous is going to be simply 30 and 30. With that, we can now build our general solution, which is x of t is a coefficient times e to the minus 0.06t times that eigenvector of 2, 3, second unknown coefficient, second eigenvalue and second eigenvector, and the non-homogeneous part, 30 and 30. Last but not least, we just need to solve for C1, C2 to match the initial conditions we were given. The initial conditions were initial concentration in tank A is 0, no salt, and a high concentration, at least relative to the incoming water, in tank B. So how does that work? Well, we just define those two values as our CACB, and on the right-hand side of our solution, we sub in t equals 0. And what does that lead us to? Well, it gives us C1 e to the 0, 2, 3, plus C2 e to the 0, 1 minus 6, plus 30, 30. That's our general solution, and now we're using it at time 0. Bring the 30, 30 to the other side and flipping things around to make it look a little more traditional. We end up with 2, 3, C1, plus 1 minus 6, C2. We bring the 30 over, we get negative 30, and bring the 30 over, we get positive 60, and the second coefficient there. And that is more easily written in a standard matrix form. C1, C2 equals negative 30 and 60. This is a nice linear system of equations. We can solve it again however we like. At the end of the day, we're going to get C1 is negative 8 and C2 is negative 14. And we would just put these values back into our general solution. We have that written out on the next page. So here's that negative 8 and the negative 14. And notice the multipliers here. This is our eigenvector in its two components, and our second eigenvector here in its two components, plus the 30 plus the 30. This is just the first row of our solution, the second row of our solution. And here we have the graphical interpretation of it. What we get in the end is that initial concentration of 90 in tank B, so this is our tank B concentration, and this line here is our tank A concentration. The tank B concentration drops well below 30 because the tank A replenishment, or its concentration, is well below 30 and it's a big vat. Eventually end up losing more salt here than we're gaining back from tank A. And then once tank B has gone below 30, then it gradually catches back up. But notice that tank A is always above tank B after we get past this region. The only way this can get more salty is if tank A has higher salt concentration. So there's still more to learn when looking at these models in terms of the details of the transition points, things like that. But now we're able to do the quantitative prediction we were looking for. We're able to predict the concentration over time for both tanks in this complicated system using a systematic solution method for non-homogeneous differential equations. Again, a very, very powerful technique.